So all of the electron configurations that we have done so far, be them full or expanded electron configurations at SPDF spectroscopic notation, or the noble gas or the condensed electron configuration, all of those that we've done so far have been for neutral elements, those species that do not have a charge. And so how do you do electron configurations for species that have a charge, specifically cations or anions? So when writing an electron configuration for a cation, obviously you are removing an electron due to the low ionization energy of that species. The electron or electrons that get removed are those that are going to be in the highest energy orbitals. And so here is where knowing your electron configuration and knowing energy diagrams and energy levels for orbitals will be helpful. So, because you can then look at the electron configuration for sodium, which is 1s2, 2s2, 2p6, 3s1. And knowing that the 3s orbital, that is the orbital that has the highest energy because it has the highest principal quantum number, 3. You know that when you write the electron configuration for sodium that has lost one electron, and it's lost one because it has a +1 charge, the electron that's going to be removed is from that 3s orbital. So that gives you the sodium electron configuration as 1s2, 2s2, 2p6. Similarly for magnesium, when writing the electron configuration for that cation that's divalent, it's a +2. The 2 electrons that are lost are from that highest energy orbital, which is in this case still the 3s. And so that leaves you with an electron configuration that is actually the same as that for sodium. 1s2, 2s2, 2p6. So we're going to talk about this concept a little bit later, but species that have the same number of electrons but different numbers of protons, those are isoelectric series. And we'll talk about that in a subsequent video. Take-home point from this slide, cations are formed by the removal of the appropriate number of electrons. Those electrons are always removed from the highest energy orbital. Now, when we get to transition metals, how do you, those guys that like to break all the rules, how do you determine what electrons get removed to form the cation? So electrons are always lost from the outermost occupied orbital, so always from the highest end level. So for example, if I had iron, if I was to write the electron configuration for iron, which I did the abbreviated here because it's kind of long, which is argon, 4s2, 3d6. Even though those 3d orbitals are of higher energy than the 4s orbital, the 4s orbital is always, it's farther away from the nucleus due to that highest end level. So when you form the divalent cation of Fe+2, the 2 electrons that are lost are from that 4s orbital, since that is the one that is outermost, is most easily accessible for those electrons to be lost. So the electron configuration, or the for Fe2+ is Ar in brackets 3d6. If I want to go ahead and remove one more electron, then it would come from that 3d orbital. And so my configuration for Fe3+ would be Ar 3d5. Okay. So when in doubt, where to remove electrons for making cations, always look for the orbital that has the highest principal quantum number, or the highest end value. Anions, there you're adding electrons. You always add the number of electrons that are designated by the charge, and those are always added to the orbital that has the highest N value. So for example, with phosphorus, if I have a neutral atom of phosphorus, highest energy orbital is 3p, and I've got 3 electrons in there. I have room for 3 more, because remember the p orbitals can accommodate 6 electrons. So those additional 3 electrons will go into the 3p orbital to give you neon, brackets, 3s2, 3p6. So that's how you write electron configurations for cations and anions. And so when determining their sizes, we use the rule that cations are always smaller than their parent anions, than their parent atoms. Anions are always larger than their parent atoms because you're adding electrons. So between calcium and Ca2+, obviously calcium is going to be larger. Between chlorine and the anion Cl negative will be larger. So you should be able to write electron configurations for cations and anions and then use these rules to determine size trends when comparing them to their parent neutral atom. I'm going to stop here. That's my little reminder. We're going to start with the last video about this concept that we alluded to earlier, isoelectric ion series.